So our main topic today is numerical integration. We're going to do this in the context of applications to statistics, as we've hinted at before. And the example we're going to consider is going to be the standard normal distribution again. Standard normal probability density function, PDF, also called a distribution. F of x turns out to equal 1 over square root of 2 pi times e to the negative x squared over 2. That is the formula for the standard normal probability density function. Do you need to memorize that? No. If you needed it for some reason and you couldn't look it up, but you happen to have Mathematica available, how could you figure it out? You could do PDF, probability density function, normal distribution. 0, 1 means a mean of 0. The graph is centered at 0. That's where the peak is of the bell-shaped curve. The 1 means what's called a standard deviation of 1. It means the inflection points are at plus or minus 1. 1 unit away from the y-axis. Comma x outside here, we'll say the variable is x. There's the formula. I can define a function f of x to equal this quickly here by just copying and pasting like this and entering. This is a function whose graph is the classical bell-shaped curve. Looks like this. It does go toward the x-axis very rapidly as x goes to plus or minus infinity. In fact, just for fun, we could experiment. What's the value of this function when x is 10? It's about 7.7 times 10 to the negative 23. How about 20? Okay, 5.5 times 10 to the negative 8, 88. Really close to 0. It's going to 0 so fast that even though the graph goes out forever and ever, the total area under the graph forever and ever is finite and in fact equals 1. That integral from negative infinity to infinity equals 1, which is what makes it a valid probability model, a probability density function. Okay, all that'll make more sense when we get to chapter 8. But for the moment, what we're interested in is finding areas under it, because that's super useful in statistics. It's done all the time. Statisticians do this. They're finding areas under normal curves basically every day, every working day. I mean, they're using technology, but we want to talk about how you could create technology to do it, even if you were going to just program your calculator to do it, or program a even simpler calculator to do it that doesn't automatically do area approximation for you. So we need to do the basic setup again. Our goal is to, let's say, approximate one particular integral, say the integral from 0 to 1 of this function. Today, that's our goal. So let's recall the basic setup of numerical integration. The A is the left endpoint, that's 0. The B is the right endpoint, that's 1. Based on a certain number n of rectangles, you would figure out what delta x is, the width of each rectangle, to be b minus a over n. So in this case, that's 1 minus 0 over n, or just 1 over n. You'd also want to figure out x sub I, where I could be 0, 1, 2, 3, up through n. X sub 1 is the right endpoint of the first interval. X sub 2 is the right endpoint of the second interval. X sub 3 is the right endpoint of the third. X sub I is the right endpoint of the ith interval. The formula, as we saw a few weeks ago, is a plus I times delta x. So for this example, that becomes 0 plus I times 1 over n. It simplifies to I over n. The left-hand Riemann sums that approximate the area onto the graph is a summation I starts at 0 and goes up to n minus 1 of f of xi times delta x. The right-hand Riemann sum to approximate the integral is the same kind of summation, except I starts at 1 and goes up to n. It is a different summation because of that, but in both cases, you're finding areas, base times height, of rectangles and adding up those areas to approximate the area under the curve. If your graph is decreasing, as our graph is here, so our graph, we're just focused on the interval from 0 to 1, is a decreasing function. The left-hand sums in that case will be giving you rectangles that are above the curve and therefore giving you areas that are too big. And the right-hand sum will be giving you areas of rectangles that are underneath the curve, and the total area will be too small. So it should make sense that then we average them to get a better answer. We call it the trapezoid rule. Trap of n is the left-hand sums plus the right-hand sum over 2. Average them. Why is it called the trapezoid rule? Because it actually does correspond to areas of trapezoids. If you connect these points with straight line segments like this, secant lines really, I'm not drawing it perfectly. It's hard to draw perfectly. Bunch of straight line segments. The trapezoid rule gives you the area of the sums of the areas of those trapezoids. Because the graph is concave down, if you draw those straight lines between those points, they'll be under the curve. And these trapezoids will have a total area that's a bit too small. When the graph is concave down, the trapezoid rule gives an answer a bit too small. If it were concave up, it gives an answer a bit too big. In any of these situations, whether you use the left-hand rule, the right-hand rule, or the trapezoid rule, you can compute the error of the approximation. And it always goes in alphabetical order here. It's the actual value of the integral minus the approximate value of the integral. The error in the approximation is the actual value of the integral minus the approximate value of the integral. This does have the perhaps unfortunate result of implying if your approximation is too big, then this difference is negative. And if the approximation is too small, then the difference is positive. Overestimates have negative errors. Underestimates have positive errors. I'm sorry, that's a little bit counterintuitive, but it's the way it is. This does have the benefit of being equivalent to saying the actual value can also be thought of as the approximate value plus the error. And I believe it's probably because we want that equation to be true is the reason we have it go like this, actual minus approximate. But this has the benefit of going in alphabetical order. Anybody in here ever open a dictionary? Right? Okay, a few people. Back when I was a young kid, 1970s, say 3rd grade, in school, we would have contests. Who can find the word in the dictionary the fastest? Okay, we had physical dictionaries and we had to think about alphabetical order a lot and sing the ABC songs in our heads as we go. This idea of error is going to be very important for us today, both for understanding what goes on with these methods and also in deriving some new methods. One of which I'll write the formula for down right now. One new method is called the midpoint rule. mid of n. It's initially defined to be a sum of areas of rectangles, just like the left and right hand rules are. But with the midpoint rule, for each interval, instead of taking the left endpoint or the right endpoint to go up to the graph to determine the height of the approximating rectangle, you take the midpoint, the point in the middle of each interval. Plug that into the function to determine the height. So the thing that changes is you don't plug xi into f. You plug, well, if I start I at 1, you plug in xi minus 1 plus xi all over 2. That number is the average of xi minus 1 and xi. Add them up, divide by 2. It is the midpoint of the interval from xi minus 1 to xi, because it's the average of the left and right endpoints. That's why. There is one more rule called Simpson's Rule, but we need to do some exploration with Mathematica before we write down the formula for Simpson's Rule. Simpson's Rule will be the best of them all. So we'll go back to Mathematica here. I would like to approximate the integral from 0 to 1. What happens if I just type that integral in here like this? As is. I don't get a number. Well, no, you do get a number, but it's not a numerical approximation. I get something involving ERF, the error function. 1/2 times the error function evaluated at 1 over square root of 2. I'm not going to explain what that means. I did hint at it like a week ago. So what do we need to do instead? Well, we could just approximate that answer. Percent sign refers to the preceding output. It's about 0.341345. We also could do n integrate instead. And as a default, that's what you're typically going to want to do. N integrate with a capital N and a capital I means numerically integrate, get an approximation right away. Like this, the function f of x, comma, x goes from 0 to 1 inside curly braces, separated by commas. There we go. It's going to be beneficial for us to get more decimal places. Okay, that doesn't work here. Let's do this instead. Okay, it's going to be best to do it actually without an integrate. It's storing more decimal places internally, but to most easily get more decimal places, let me do this. Let me put the integral sign inside the capital N and say put a comma 20 to see 20 decimal places of accuracy. By the way, you can easily like do 2,000 places of accuracy if you want as well. Okay. The true answer is an irrational number whose decimal expansion goes on forever and ever without a repeating pattern. All right, let's just do 20. Okay, so you have to approximate it in the end if you want it to be of any use, at least. In some way, you have to approximate it. All right, let's program Mathematica to do the left, right, and trapezoid summations first. Remind you how that's done here. Type in A, type in B. If I do it this way, it allows me to make changes to A and B if I want. Though if I do make those changes, I need to re-enter the code. Left of n, it's a function of n, so I put the underscore in there. Summation button, I goes from 0 to n minus 1, f of something times delta x. But if I'm going to use that in a useful way, I got to define delta x. And delta x really depends on n, so I need to really specify to Mathematica delta x depends on n like this. I need to put the dependence on n here as well. What's left is to type in xi. Well, that's a plus I times delta x. You can type it like this. This is Mathematica version of that formula right there, with xi being a plus I times delta x. And yes, again, I'm emphasizing I'd like to be able to change n. That's why I'm writing delta x as a function of n. It depends on it. Once I got that typed in, I can do the right one pretty quickly because I can copy and paste. The semicolons technically suppress output, but you can also think of them as separating the different lines of code here, the equations. Change the 0 to a 1, change the n minus 1 to an n, and then you have right. Trap is going to be the average of those two. Let's also program the midpoint one now. Copy and paste this, but then make appropriate changes. I need to change what goes inside there. I did this with the first class. I'll do it again with you. You actually can write that midpoint in terms of a and delta x. I think it's worth doing once. Not that you always have to do this. xi minus 1 is a plus I minus, whoops, a plus I minus 1 times delta x. xi is a plus I times delta x. It's all being divided by 2. We've got 2 a's. That gives you 2a. And if I combine these two expressions that both involve delta x and factor out the delta x, we got an I in both spots. So I'm going to get a 2i. And then I have a minus 1 as well. 2i minus 1 times delta x, all divided by 2. That's one way to write the midpoint. I mean, it is the way to write the midpoint in terms of a, I, and delta x. So I'll type that in here now. I'm plugging that into F. I'll go ahead and type it in as is, 2a plus, in parentheses, 2i minus 1 times delta x. But delta x depends on n, so don't forget the of n, all over 2. All right. Going to enter all this. What we're about to do is the most important part of today's class. So listen really carefully. You can write some things down, but it's probably going to be more important to listen. Any one of these things could approximate the value of the integral. I could do with n equal to 2, for example, left of 2, right of 2, trap of 2, and mid of 2, and see how they compare with the integral, which I'll type in, I'll copy and paste that number there. Although it does something funny when you do that. It adds more decimal places. It also does this at the end. It's kind of weird. Okay, that ends at the 9 there. I'll go that far. I'll get rid of that. We also want to do numerical approximations for all these things. So I better do the / capital N. And maybe I want more decimal places of accuracy for those too. Sorry, hang with me here. Okay. Oh, and Mathematica shortened that one. Okay, well, take a look at these numbers. What's going on here? There's the quote unquote best answer. Focus on it up there. Let's just retype it here. What's closest? Midpoint rule's best. Left and right are worst. Trapezoids in between. Almost as good as the mid. The left-hand rule is too big, right? We made a drawing of that. That was this drawing. because our graph's decreasing, the left-hand rule is too big, the right-hand rule is too small. Trapezoid rule I did mention, because the graph's concave down, is a bit too small. That number is a bit too small compared to the best answer. Looks like the midpoint rule is a bit too big. Why is that? Without giving you an explanation, the midpoint rule can also be thought of as areas of trapezoids, actually. But they're not the same trapezoids as the trapezoid rule. And we don't think of them as trapezoids initially. We think of them as rectangles that come from using the midpoint, like when n equals 2, looking like that. But you'll see this in the reading in the book. You can rotate the tops of these rectangles so that they become tangent lines to the red concave down curve. And the resulting trapezoids have the same areas as those rectangles. And because those tangent lines are above the concave down curve, those areas are a bit too big. Now that requires more explanation than I gave, but that's the idea of what you'll see when you do the reading, as you should. So the midpoint rule is a bit too big. What about the errors in these things? Let me take these numbers. And in each case, let's subtract them from the quote unquote actual value. So I'm going to put the best approximation in front with a minus sign for each of these. I'm computing the errors now, actual minus approximate. Actual really in quotes, because even that 20 decimal approximation is still an approximation. What do I get? I get some numbers close to 0. The negative ones, actual minus approximate, correspond to approximations that are too big. The left-hand rule and the midpoint rule were too big. The positive ones, for right-hand rule and trapezoid rule, those were too small in their approximations. But they're all pretty close to 0. The closeness of these numbers to 0 measures how well the approximation does. These are further away from 0. Left and right are worse. These are closer to 0. Trap and mid are better. The signs of left and right are opposites. The signs of trap and mid are opposites. The absolute value of left and right are in the approximate ballpark of each other. They're not exactly the same by any means, but they're in the ballpark of 0.04, both of them. That's kind of why, numerically speaking, it makes sense to average them with the trapezoid rule to get a better approximation. What about the absolute value of the errors from the trap and the mid? Look at that. The mid is better. It's closer to 0. And in fact, ignoring the minus sign, it's about twice as close to 0. The midpoint rule for n equals 2 is doing twice as good, approximately, as the trapezoid rule. Let's try doubling n to 4. So I'm going to change all these 2's to 4's here now. Increasing the number of rectangles or trapezoids to 4. How do the errors behave? The new errors are even smaller. Notice the new error for the left-hand rule has the same sign, still negative, and is in the ballpark of half as big, twice as small. Same kind of thing happened with the right-hand rule. There's the first error. Here's the new one. Same sign, about half as big, roughly speaking. With the trapezoid and mid, still the same sign in both cases, but now the errors are not half as big. They're 1/4 as big, approximately. 0.0125, close to that, compared to 0.005. This is about 1/4 the size of this. Same kind of thing happened over here. This is approximately 1/4 times that, right? 6 times 4 is 24. It's in the ballpark. Is that a coincidence? No. That always happens. If you double n, multiply n by 2, and recompute, the errors for left and right go down by about a factor of 2. The errors for trap and mid go down by about a factor of 4, 2 squared. If that pattern holds for not just doubling, but say multiplying by 10, what's going to happen? So now I'm increasing down here to n equals 20. If the errors got cut in half for left and right when you doubled n, they should get cut by a factor of 10 when you multiply n by 10. And if they got cut by a factor of 4 for trap and mid when you doubled n, 4 is 2 squared, they should get cut by a factor of 10 squared for trap and mid. So effectively, when I'm entering these numbers, it should be similar to these numbers, but with an extra 0 for the first two, and an extra 2 zeros for these. Let's see if that happens. Yep, compare. 2 zeros there before the 3, just like 1 0 there. 2 zeros there before, well, close enough to 4, just like the 1 0 there, one more. Instead of 2 zeros here before the 5, we now have 4 zeros before the 5. Instead of 2 zeros before the 2 there, we got 4 zeros. Yes, that happened. Trap and mid went down by a factor of 10 squared, a factor of 100 in the size of the error. Much, much smaller. And once again, the error for mid is about twice as close to 0 as the error for trap is. And therefore, that's why our final rule, Simpson's rule, is defined to be a weighted average of trap and mid, giving mid twice the weight because it does twice as good as trap typically. Meaning we add up 2 values of mid and also 1 value of trap and divide by 3. We're averaging 3 numbers really. When you add up a number with itself, it's the same as multiplying it by 2. So we do 2 times mid of n plus trap of n divided by 3. If I do n simp of 20, the 20 decimal places, it should be really close to this best approximation. To fewer places. How much do these agree? They agree this far. Pretty good. If I try to do the error calculation, actual minus approximate, on the order of 10 to the negative 9 when n is 20. What happens as you increase n with Simpson's rule? With n equals 2, the error is still pretty small. Negative 0.000000001. About negative 10 to the negative, what would that be, 5? What happens if I double n here? The error goes from on the order of 10 to the negative 5 to 10 to the negative 7. Okay. More importantly, that thing is in the rough ballpark of 16 times smaller, 2 to the 4th power. Multiply that by 16, you get roughly in the ballpark of this thing. If I multiply n by a factor of 10, from 2 to 20, again, this was like 10 to the negative 5. The error is going to go down by a factor of 10 to the 4th, 10,000. We'll get 4 more zeros in the error after the decimal. Should be on the order, instead of 10 to the negative 5, of 10 to the negative 9. Yes. So I'm stating principles here without writing them down. These principles are in the reading. You should definitely carefully do this reading, even if you've never read to this point in this class. Carefully read section 7.5 to understand these general principles. It's definitely going to be beneficial for your homework. The homework does involve not just basic approximation problems, but conceptual problems that are kind of tricky. They involve doing some problem solving using these principles.